So, hello to everyone. It's a great opportunity today for me to have a chance to have this talk, and for our colleagues from VIAS and for everyone who is for the first time in Moscow. So I wish you to have a great time in Moscow, sightseeing, visiting interesting places, and have a great time after our short conference. So I will try to tell you about our joint work with Vladimir Spokojny. It's research in progress, and there are some open issues and interesting open problems and topics. Nevertheless, we have some interesting results. At first, I begin with motivation. So we are working with statistical models where parameters are identified by some kind of conditional estimating equations. You can, so everyone who is familiar with method of moments or generalized method of moments can look at this problem and try to apply kind of these techniques to this one. But this topic is a bit more general because here we have conditional restrictions, so we have this kind of equations which are almost surely zero at the true point. So some simple examples: linear and nonlinear regression models, conditional quantile models, and some other econometric models. And our target is to estimate the true parameter if parametric assumption is correct, yes, and get confidence bounds for our estimator. So mainly we are interested in getting confidence bounds because estimation of parameters in such models, so it's a very developed topics. There are a lot of papers, a lot of techniques, and we are working more with theory, so it's kind of motivation. Assume that we have moved from a conditional restrictions to an restricted case. So we have some simple problem. We try to build a quadratic form over our observations. So Vig is a kind of elements of positive semi-definite matrix, and we are trying to build a simple estimator. So at first we are choosing this kind of elements of the semi-definite matrix. As far as you know, usually the elements are chosen based on data. So, and if you are familiar with generalized method of moments, you know that the optimal, the optimal matrix, which gives an efficiency to this estimator, really depends on a real measure. But in our problem, we try to look at this matrix as a fixed, and we have no randomness in it. So we are working simply with, so all randomness comes from gi thetas, and Vig is fixed in this problem. If we look at this equation, we can simply calculate expected value, as you can see, and we have so non-stochastic part and expectation of stochastic part here, and so simple decomposition is Vi is an expectation. So Vi is an expectation of these elements which we have from our equations, and epsilon I theta is a kind of centered random stochastic part. And as you can see, if this matrix is positively semi-definite and parameter assumption is correct, we have a true value which minimizes this kind of expression. But we don't know anything about the I theta, yes, and we have only our estimator, so we can build just this random construction, yes. So here we introduce our estimator. So we are building this m theta from the previous slide, and we are normalizing it by the expected value of our stochastic part. So some simplifications we have, for example, that matrix WBIG is a symmetric matrix, so it's positive, and we have a square root of it, so we denote it as A. And another convenient simplification that expected, so variance of this squared, variance of our stochastic part is constant over whole set of parameters. How to, so we're trying to get some results about this problem, but we have a lot of difficulties because here we have to get results uniform, or the set of parameters and stochastic part is really difficult to analyze. In this case, we are trying this kind of decomposition and simplification. We introduce G theta 0 in where we have a fixed point for our stochastic part. So, and we define another quadratic form, or where we have, instead of E theta, E theta star, so with fixed point. And one can show that this kind of simplified problem has the same optimal point. So we are moving from a lot of points from the stochastic part, so all our vicinity, yes. And we finally arrived to a simpler problem with the same optimal point, or true point, theta star.
May I interrupt a little bit just to tell us a short story? Actually, this is not a technical trick. It's there is a history of this project. Originally, we tried to work with the original quadratical form because the estimator for this conditional movement restriction approach is defined by optimizing some quadratic expression. And if you want to apply the theory, so you need some kind of smoothness of this quadratic expression with respect to the parameter. And it should be smooth in the mean and smooth in stochastic part. But it turns out that the original quadratic form is not smooth enough in the stochastic part. And so the theory actually doesn't apply at all. And what we realize, so if you replace it by this L0, so somehow you kill the dependence on the parameter in the stochastic path in the quadratic term. This quadratic form is extremely high to study in the full generality. And so we apply this trick, and we will see how much you pay for this. You can still do the study, but you have another rate at the end.
Yes, so thank you for this comment. Yes, we have replaced stochastic process of this stochastic part with simply one random value, or random vector, something like this. And we start with some conditions, so simple conditions. First, we fix AD0, so it's all about sub-exponential moments of E theta 0 at this optimal point, and some conditions of the gradient of this vector component wise. So during these slides we have a lot of G and G squared symbols, but if you have a lot of conditions, so you can always choose the minimum of them, and so you will have no problems with it. We define Fisher information matrix for L0 theta star, so we will work mainly with properties of L0 theta star instead of L theta, which is defined. So I remind you that it's our true value or true likelihood, and here we doesn't have this star. We have a full process, which, as Vladimir have told already, and we have analytic set. So we are working uniformly, and this Fisher information matrix gives us some kind of normalization for definition of this vicinity of true central point or true point if parametric assumption is correct. So when we have L0 theta, we can, so it's based on our data, yes, it's some random construction, we can define this kind of theta brief. So it's an estimator of L theta 0. And our estimate of interest is this kind of theta, which maximizes the true L theta. And at first we show that under very mild consumptions with high probability, this L theta brief, L0 theta brief is close to this L theta tilde with high probability, and this residual term is small. So a few words about conditions that a bit bulky, but okay. Okay. So they are a bit bulky, but nevertheless they all have a simple structure. So we're working with some sub-exponential conditions, some vectors, so matrices, our likelihoods or gradients of likelihoods. And for example, D property is used to apply generic chaining method to upper bound our stochastic process uniformly, and E2 is more gradient-based property, which gives us our Wilks expansion. So I will tell about it later. And two more very important conditions. So one of them is L1. It gives us an information about that AB theta is continuous around our optimal point, and this kind of conditions this condition is also very important. It gives us a chance to introduce a result about large deviation bounds. So we formalize it on this slide. We have a lot of conditions. We have very mild condition on our weighting matrix. We have a small condition on the previous parameters, and if you have this kind of property for BR, so BR comes from this. We have, with a high probability, a very small probability of simultaneous, so we have a very small probability that two of our interesting parameters of interest are out of our local vicinity of true point. So I won't write all the formulas here, but in some sense you can look at this as these asymptotic forms. Nevertheless, all results are not asymptotic. So we finally come to one of our main results. It's just direct usage of techniques from our theory gives us some kind of Wilks expansion for L theta, because all the L theta, no, L brief theta, theta star 0. So it's a kind of because we have all previous conditions for L0, yes, that's why we have Wilks expansion for this kind of expression. So it was, these symbols were introduced before in conditions. So any questions to this moment?
So just a comment. So I mean, it's nice theoretical result, but it's practically useless because L0 is not available. So what it basically says that access for in existing process L0 is nearly chi-squared.
Yes, L0 is something like proxy process. Yes. So we have, if we want to construct it, we have to know the true point. So, and we don't have it at all. But it's it's a major step in our analysis. So it was a huge effort how to prove that L theta and L theta 0 are close to each other, and the simplest is the best as usual. So we use a triangle inequality, and somehow we understand that the difference between them, so this times square root of them, is controlled by this kind of process, and this is the difference of epsilon theta epsilon theta star. And then the next problem for us was how to bound this uniformly. We had a branch, have a lot of results. One of them are more bulky, one of them are simpler, one of them correct, one not at all. But finally, after half a year or even more, so we spent a lot of time in it, and we had some final form for this. So we have this kind of conditions over vicinity which is not normalized by D0 as previously. We have one of conditions over epsilon theta, and we have that with high probability we can control norm of this process uniformly over all our vicinity, and it depends on properties of matrix A this way, of size, of data, of size of our sample, and H, as you can remember, is a parameter which we used in our kernel when we built matrix A and matrix A. So next slide presents our main result.
But what is the log of A squared? There's a trace of A something, and what is the log of A squared?
So it's a logarithm of matrix. You can.
And then you take trace.
Yes. If everything
Trace is outside.
Yes, trace is outside. So if everything is okay, you can just write an expression, Taylor expression for this, but it's not the best form. So you can diagonalize the square, then try to apply logarithm to singular values, etc., etc. So it's calculated. And our final result gives us, under all the previous assumptions, a lot of them, but we have this kind of results. So we can control, or we have a Wilks expansion for our true parameter, or for our observable L instead of L0, and it's concentrated highly around this kind of thing, which has so which is like expectation, or which has a chi-squared distribution asymptotically. And these terms control our true deviation, so they depend on properties of our matrices and depends on our rate of interest, so with high probability, this is residual term. This kind of term comes from L0, yes, and this kind of term controls the difference or the maximal difference between L0 and L over all set of integers. So I'm not also writing these expressions, but they have all great or good rates. And finally, some discussion. Okay.
In order of the full dimension of the problem, what is the scale or the size of these trails?
So this one
This one is square root p or cube over n.
yes. So this kind of results has the same properties. So this triangle first, yes, has the same property as in general Wilks expansion, so p n squared, and this kind of result it has a bit another structure because or nature, because it controls how our process so how we change our process by changing epsilon theta by epsilon theta star, and so in bad cases it can have worse rates, but nevertheless we have a good rates over n. So in this case, so these rates are even better than in this problem here, and this is also a small term, but as I told, it's a research in progress, and some estimates are there, and there are some open problems, so they are to analyze, to be analyzed. And one more thing about discussion conclusions. So here we have mild assumptions. We have Wilks expansion for L0 theta. We have so Wilks expansion for L theta, and but we don't have a Fisher expansion for this model because or good Fisher expansion because we cannot apply directly results with square p squared divided by n because we were working with L theta and L theta null. So if L theta and L theta 0 are close, we nevertheless don't have information that theta brief and theta this theta are close. So if two functions are close, we don't know whether their maximizers are close. So it's a problem. And in this area, we have to use our previous results or a bit old techniques, which give us the same rates as in this problem. So we're interested if we can somehow improve and have a Fisher expansion with better rates than in the previous situation. So it's still a local problem and research to do. So thank you for your attention.
Maybe I also comment to this last comment. It's actually a big class of problems. You can think about something like binary regression, when you don't use like logistic regression. You work directly with the residuals, and residuals are binary random variables. And then you somehow center the residuals and build some quadratic form of this centered residuals, and this is very unsmooth process. And if you want to apply the theory, you realize the process is not good enough. At least stochastic part is not good enough. Expected value is okay, but stochastic part no. And what we are doing, we approximated this process by another one, which is smooth. It's L0 process. It is smooth in theta, and you can do the whole theory for this smooth process. It's fine. But, and you can also do Fisher for this smooth process. It's very nice, and Fisher means some expansion for the gradient. But you can approximate these two processes well, but you cannot approximate the gradient of the process well. And therefore, it doesn't apply for the point of maximum. And therefore, for the point of maximum, we have the same accuracy as the value of maximum. Not better. So somehow it's not direct way because Wilks in direct theory is applied from Fisher, but here is Fisher from Wilks. So this is the only way we found for this problem, but probably the problem is generic, so you cannot improve. At least for this special case of binary regression, binary response, it seems to be not possible to improve. Okay?
So do the classical maximum likelihood estimator results apply in the sense that there's a differentiability in quadratic mean of the...
Yeah, no problem with maximum likelihood. If you do generalized linear for logistic regression, everything works fine. It's just because you built very special quadratic expression and you define your estimated direct from the residuals. And the residuals are not from logistic regression. The residual is just indicator minus its expected value. It's very unsmooth in the parameter, the stochastic part. And you do it squared and optimize, and your point of maximum is extremely irregular. So this makes the problem difficult to study. So it's unexpected technical problem. We really spend the time to come over. Further questions? Okay, if not, thank all the speakers.